Okay, so now next reaction is Appel reaction. In continuation with the another previous one, Berry-Silman or Morita-Berry-Silman reaction. We'll see one by one what is the Appel reaction. So first one here, Appel reaction is very important reaction for synthetic point of view. So here is the general reaction. Alcohol we have to transform into the alkyl halide. Okay, so uh, transformation of alcohol to alkyl halide in presence of any halogenating solvent. Okay, CCl4 we have taken, or CBr4 we have taken here in presence of triphenylphosphine as a catalyst. Okay, so in previous example in Bailey-Silman reaction we have used DAPCO as a nucleophilic catalyst. Here also this triphenylphosphine is also nucleophilic catalyst, and we are going to use this triphenylphosphine to convert this alcohol to this alkyl halide. So overall reaction is just we have to remove this OH and we have to attach chlorine at the place of OH. And this stereochemistry of this reaction is this inversion of stereochemistry. So as starting material, it gives the inversion of stereochemistry. So obviously this reaction, this is substitution reaction, and this is nothing but the SN2 substitution reaction. So nucleophilic substitution reaction, nucleophilic bimolecular substitution reaction, which gives the inversion of the stereochemistry. That is nothing but the you are getting stereospecific product as a alkyl halide. Okay, so we'll see one by one what is the mechanism and what things involved in the Appel reaction. So Appel reaction is more or less similar to the one of the important chemical reactions called Mitsunobu reaction. Okay, so you can search for the Mitsunobu reaction, in which combination of phosphines, a diazo compound acts as a coupling reagent, and a nucleophile is used to alter the stereochemistry of an alcohol or displace it. So Appel reaction is resembling to the Mitsunobu reaction. In Mitsunobu reaction also we do use phosphine as a catalyst in combination with the diazo compound. Okay, so this is the additional information. Now we will see the mechanism of the Appel reaction. So Appel reaction is an organic reaction used to convert an alcohol to an alkyl halide using a tetrahalomethane and triphenylphosphine as a catalyst. Okay, so as we are going to use tetrachloromethane and triphenylphosphine, so definitely there will be reaction first in between these two reagent, tetrahalomethane and triphenylphosphine. Okay, so we have to react these two first, and whatever things comes out from these two reaction, from these two reaction of these two reagent, then that intermediate we can utilize for the next conversion. Okay, so the reaction begins. So starting material we have now reagents trichloromethane or CCl4 and tetrachloromethane and triphenylphosphine. So triphenylphosphine acts as a basic catalyst because phosphine has one lone pair. So this lone pair, what that one is doing, the reaction begins with the halogenation of triphenylphosphine followed by the formation of alkoxide from the alcohol starting material. Okay, so we have to do first the reaction in between CCl4 and triphenylphosphine. How to do that reaction? So reaction proceeds by activation of the triphenylphosphine by reaction with the tetrachloromethane. Okay, so we will see now how to activate the triphenylphosphine by CCl4 and how that one reacts in the further. So here I have given mechanism. So clear cut mechanism I have written here. We will take some shortcuts, but here you can come to know that each and every step what I wanted to explain you, how the SN2 attack occurs and how the inversion of stereochemistry occurs. So first step we have used here triphenylphosphine with tetrachloro halogen. Okay, so that means CCl4 carbon tetrachloride. So reaction in between these two, that means that is nothing but the activation of this triphenylphosphine. Okay, so we have to activate this triphenylphosphine by treating with carbon tetrachloride. So here the reaction gives as phosphorus this it abstracts one of the halide from this tetrachloro compound. So here you can see this lone pair which is present on the phosphorus atom abstracts halide from Cl plus from the CCl4, and it eliminates CCl3 minus. Okay, it eliminates the CCl3 minus, and we will see now how to react this CCl3 minus for the next step. Okay, so we got now CCl3 minus by activation of the triphenyl phosphine. So so once this triphenyl phosphine abstracts chlorine, here is the formation of one positively charged moiety. So this positively charged moiety, now we again we have generated this CCl3 minus. Okay, so we have generated negative moiety also. So now what this negatively charged moiety, that one species, that one is doing, so that negatively charged species, that one is abstracting proton from the our starting alcohol. Okay, so we what is our need? We have to replace this OH group by Cl group, any halide group. Okay, so this is our target. So first step we have done here, abstraction of proton from this hydroxyl group by this CCl3 minus. Okay, so to generate this alkoxide ion. So now we have two species, charged species in our hand. One is phosphorus with positively charged phosphorus, this salt, phosphorus containing salt, and another one is alkoxide ion. So with the elimination of chloroform, here CCl3 minus is converted by abstraction of proton from the alcohol, that one is converted to the chloroform. Okay, and now in our hand we have two charge species, one is positive charge, one is alkoxide ion. So now we are going to react these two with each other. Okay, so now once we got alkoxide ion, it will attack this, acts as a nucleophile, and this nucleophile will attack on the positively charged phosphorus atom. So there is a formation of oxygen phosphorus single sigma bond. You can see over here there is a formation of sigma bond in phosphorus and oxygen atom with elimination of Cl minus. Okay, so Cl minus we got eliminated over here, and now here we got one intermediate in which there is a bond in between phosphorus and oxygen. So okay, so this bond is very helpful bond to remove this oxygen atom. Once we got phosphorus and oxygen bond, our half of the work of half of the reaction has finished already. So now the last step is elimination of oxygen atom in form of the phosphine oxide. Okay, so what is the exact use of triphenyl phosphine as used as a reagent? That triphenyl phosphine is converted or abstract this oxygen atom from the alcohol, and that one is converted into the phosphine oxide. Okay, this phosphine oxide is as a waste. We have to we can eliminate this phosphine oxide from our reaction mixture. Okay, so how to eliminate this phosphine oxide? So once we generated phosphorus oxygen bond, so we can now this lone pair which is present on oxygen, that one is shifting in between this phosphorus and oxygen to form the phosphorus oxygen double bond. So once phosphorus oxygen double bond has generated, positive charge is shifted on oxygen atom now, and as triphenyl phosphine oxide is highly bulky molecule, pay attention that three phenyl rings, they are attached to this phosphorus atom. So that one is highly bulky. So as that one is highly bulky, that one is definitely, that one is trying to eliminate. So now here once we got phosphorus oxygen double bond, it's not easy to break this P double bond O, but it's better we can break this carbon oxygen bond. Okay, so in this way this carbon oxygen bond sigma bond is breaking, and this lone breaking, and or we can say shifting on the oxygen atom. This lone pair is shifting on the oxygen atom, and this SN2 attack is already generated Cl minus. Okay, the Cl minus already generated in our reaction flask. This Cl minus is attacked from the backside. Okay, this is SN2 attack. Okay, this Cl minus is attacking from the backside, and as that one is attacking from the backside, automatically this lone pair in between carbon oxygen shifting on this oxygen atom, and this triphenyl phosphine oxide is getting eliminated as a side product. Okay, so here we got eliminated phosphine oxide, triphenyl phosphine oxide, and we do form the new carbon halogen bond with the inversion of the configuration. So Appel reaction is nothing but the nucleophilic bimolecular nucleophilic substitution reaction with inversion of configuration, and Appel reaction is nothing but the stereospecific reaction, because we do get 100% inversion of the configuration of the last product. Okay, so this is stereospecific reaction, as that one is SN2 reaction, and this is we got 100% the final product with triphenyl phosphine oxide as a uh, waste material. Okay, so this is the clear cut mechanism, point to point representation of each and every step. So better that one would be very helpful to refer this one. One more reaction mechanism I have displaying here. So this is also the same thing, but it's not clearly mentioning all steps. So first step, activation of this triphenyl phosphine by abstracting chlorine from the CCl4, one equivalent, one equivalent, both are one equivalent. So now once we generated CCl3 minus, okay, CCl3 minus we generated, that one is abstracting proton from this starting material alcohol, that one is also one equivalent. So we have now this type of positively charged phosphorus atom and negatively charged alkoxide ion. This alkoxide ion attacks on the positive charged phosphorus atom to form the phosphorus oxygen single bond. Okay, eventually how the phosphorus oxygen double bond is forming, and how this triphenyl phosphine oxide is eliminating. Again, chloroform is eliminating. Okay, so byproducts are chloroform is byproduct and triphenyl phosphine oxide is byproduct, and our targeted product is this carbon chlorine bond formation. So halogenated compound we got from the alcoholic compound. So replace this substitution of OH group by halide group we got in this way. So you can refer any of this mechanism for your study. So triphenyl phosphine oxide or triphenyl phosphine, see both these reagents, they are versatile reagent. Nowadays we can in Mitsunobu reaction also we do use the same reagent. See what is the beauty of this reagent triphenyl phosphine. This triphenyl phosphine oxide we can reduce in situ. Okay, and again we can use for the next reaction. Okay, so this triphenyl phosphine oxide we cannot say this one as a waste or side product. So this is very useful product. We can reduce from phosphine oxide to again phosphine, and this is recyclable organocatalyst. Okay, this is considered as an organocatalyst, and we can, by reduction of this phosphine oxide bond, we can reduce this triphenyl phosphine, and we can utilize this for different reactions. Okay, so this use of phosphine is very important in organic synthesis. Now what are the applications of the Mitsunobu reaction? So I'm trying to explain over here applications of these Appel reactions. So Appel reaction is used to formation of alkyl halides, which are molecules consist of carbon and at least one halide. So commonly known and used alkyl halides includes one chloroform. We have seen just on previous slide, chloroform is the byproduct. Chloroform was previously used as an anesthetic, but later it was found it causes cancer. So we are not using nowadays as an anesthetic agent. So 2-carbon tetrachloride, second application, CCl4 formation. Carbon tetrachloride is found in some dry cleaning solvents, fire extinguishers, and can be cause liver damage. Okay, so but there are disadvantages also of these chemicals. It should be there. Third application, chlorofluorocarbons we can synthesize. So CFCs we can use in refrigerants for the cooling, as a cooling agent, air conditioners. Okay, refrigerants, air conditioners, we do use chlorofluorocarbons, but more recently have shown to deplete the ozone layer. Okay, so disadvantage of these chlorofluorocarbons are they destroy the ozone layer, and different aerosol inhalers and like that. Okay, so different applications of these Appel reactions and different things we can synthesize as a chlorinating agent, and we can use this Appel reaction as a chlorinating agent. So I hope this one will be helpful for you for your final examination.